All right, so put all your distractions away. Let's have a quick look. So we'll talk about this. The topic that we're just going to be starting with explains how to build Julia sets. And this is just one example of a Julia set. This is the Mandelbrot set. So it's not really complicated stuff, but we'll get there. We'll get there. This will be kind of a fun, like maybe a Friday little demonstration. I've got, and there's a interest, if I can find it, there's a really kind of a cool video that goes with this, I think it's a Nova or something that talks about some really interesting applications of fractals. And this is just an example of a fractal, of a really kind of a complex fractal. Okay. Here's where we start, though. Here's where our journey begins today. Whoops. Okay, so we can solve this, right? This is no big deal. We've been doing stuff like this, solving quadratics where we can point to a single variable by just using inverse operations, right? So what are the steps here? What's the first step to solve for x? Add 5. Good. Okay, so first things first, and then that's going to give us negative 2x squared equals 18, right? Now what? Divide by negative 2. Okay, and those guys cancel, and we end up getting x squared equals negative 9. Now what? Square root. You see a problem with that? Yeah, what do we always say? We got two rules, right? You can't divide by what number? 0. And you can't take a square root of. Okay, but the rule actually didn't say you can't do it. It just said you can't do it and get a real result, right? You can't divide, you can't take the output of a square root of a negative number is not a real number. And every number you've ever dealt with in your entire life has been a real number. So up until today, we were just able to say, no, you just can't do it. But today we can. Today we can. If we square root both sides, if I square root, and our procedure still, the process is still the same. If I square root both sides of an equation, what do I have to include? Plus or minus. And then now I've got the square root of negative 9. Okay, what we're going to do here is we're going to write this, we're going to break this up into, there's a problematic part of that square root and there's a part that's not. I could break the square root of negative 9 up into, and I'm using my property of, what do I call this? I think it's the root of a product property. So if we do square root of a times b, remember this property, I can split that up into a product of separate square roots. So I could write this as x equals plus or minus the square root of 9 times the square root of negative 1. Okay, square root of 9 is fine. What's that? 3. Yeah, that's no big deal. What about the square root of negative 1? Now, there's no answer to that you're aware of, but it turns out the square root of negative 1 is defined as the imaginary unit. Okay, so if we go to our notes, I think that's what we got on the next page. Yeah, we'll duck here, and then we'll come back and we'll look at some applications of this again later. The imaginary unit, I, is just defined as the square root of negative 1. Okay? It's just not a real number. Now, it's really unfortunate that, well, here, let's, This is useful when working with square roots of negative numbers, obviously. Okay, so a pure imaginary number is written in the form b times I, where b is the imaginary part. Now, the way they've got the notes, I had to change this. So if you look at the published version of the answers to the notes for today, they're going to be incorrect. The notes are not written correctly. This textbook doesn't quite do it right. But b is the imaginary unit, and a pure imaginary number is just going to be, is the imaginary part. B is a real number, okay? B is a real number here. I is the imaginary unit. Okay, the only imaginary number that we ever really deal with is I, the square root of negative 1, which we can multiply by any coefficient we want to. Okay, and we create what's called imaginary numbers by multiplying real numbers times I. Okay, imaginary number is a really, really unfortunate name for this, because you tell me, if we're talking about real numbers compared to imaginary numbers, which one sounds more concrete and useful? Yeah, real versus imaginary. It's a terrible, terrible choice of a name, because it makes it sound like real numbers are concrete and useful and imaginary numbers are fluffy and made up and they don't mean anything, right? Well, first of all, let's just get this straight. All numbers are made up. There's nothing, we've talked about this before, there's nothing real about a real number. A real number is just it's a symbol applied to an abstract concept. What does it mean? What does 3 mean, right? 3 doesn't really mean anything. 3 is a concept of cardinality. You're going to ascribe some property to a group of objects based on what we call the number of objects in that group, right? But any number is purely abstract. It really doesn't mean anything. It's useful, but it's like all math. It's just completely abstract, okay? So real is a misnomer there to begin with. And imaginary numbers are just as useful. In fact, when you get into like electrical engineering, before I taught, I was an electrical engineer. My major is physics. So if you look at physics or electrical engineering, you get to a point where you use probably more imaginary numbers than you do real numbers. It just, I mean, they almost everything you deal with, like when you get a couple, 2 or 3 years of math under your belt, and you start to look at some more advanced math stuff, I mean, everything is just complex. Complex means it includes imaginary numbers. All the analysis you do, all the calculus you do, all the differential equations, all of it includes imaginary numbers all the time. Okay, so it's eventually, when you continue with math, and I hope you all do, you're going to see a lot more of these. You know, this year we just kind of scratched the surface a little bit. But it's not hard stuff. I promise you it's not. Okay, so we'll talk more about how we represent these things and what they do for us later. Let's just practice using them for a second. Okay, so if we want to simplify negative square roots, well, what do we always do? Here are the steps we go through. Okay, we're going to rewrite the negative square root as a square root of negative 1 times a positive number. And then really there's another step that they should include here. Let's add this to our notes. And then we would write that as the square root of negative 1 times the square root of a. And the square root of negative 1 is equal to I, right? So if we take an example like here, let's see, what do I got behind? Oops. What have I got behind here? I can't remember. Okay, and we'll get to that soon. Let's just look at a couple quick examples. And I think I've got some. No. Okay, we'll just pick a couple off of your sheet here. Like let's look at the square root of negative 9, okay? Square root of negative 9, we could write as the square root of positive 9 times the square root of negative 1. Okay, well, what's the square root of 9 equal to? 3, right? So this is just equal to 3, and what's the square root of negative 1 always defined as? I. So we could kind of take a shortcut here. whenever we see a negative inside a square root, that's always going to end up becoming an I outside the square root. Okay? And then everything else is the same. The square root of 9 becomes a 3. Okay, so what about this one? The square root of negative 196. This really only adds a tiny step to the stuff we've been doing. What's this negative going to become? It's going to become an I, right? I got the square root of negative 1 times the square root of positive 196. So the negative part is eventually just going to tack an I into my answer, right? I'm going to multiply my answer times I. What's my answer? Just a regular old square root of 196. If I make a factor tree out of 196, let's see, can we be smart about this? I want the left branch of my factor tree to be the biggest perfect square factor I can find for 196. Okay, 196 is not a perfect square, so we can look at half of that. Well, half of that would be, what, 48? Anybody agree? Is that right? Or no, sorry, 98. 98, sorry, not 40. 98. So 98 would fall right in here, wouldn't it? Okay, just a little less than 100, but more than 81. So now we'll just look up from there. We'll just work our way up the list until we finally get a hit, if we do. If we get one that divides evenly into 196. Well, 81 does not, right? Agreed? Okay, 81 doesn't work. 64, does that work? No, no good. Wait a minute, does 64? Going to 196? You sure? Oh, no, I guess it doesn't, does it? No, it doesn't. You're right. 64 doesn't. Does 49? Ah, it does. Times what? 4. There we go. Okay. So we could break the 196 up into a 49 times, what did we say it was? Oh, you know what? Well, then you know what that means. We missed one. We just didn't take our list far enough. 196 is, in fact, a perfect square. It is a perfect square. It's 14 squared, guaranteed. How do we know that? Did you say that? Oh, it is, and I should have known that. I should have recognized that, but I didn't. How do I know that? Because both of those are going to be couples, aren't they? Right? So this gives us a couple of 7s, and this gives us a couple of 2s. So there's no singles. Couples go out and there's no singles, right? So we end up with a 7 times 2 outside, so that's 14. So what's this work out to be? 14I. Right? Okay, let's pick one that doesn't work out quite so nicely. How about 32? Why not? Square root of negative 32. Okay, what's the negative going to give us? An I. And let's look at the 32. Perfect square factor of 32, biggest one? Say it again. 16 would work, wouldn't it? Yeah, 16 and 2. And the 16 is going to break up into a couple of 4s. And the 2 is going to be my single. Right, so we're going to get a 4 times the square root of 2, and then we're going to get this I. Okay, that's our answer. Now, a lot of times what we'll do with the I, do you see just a practical danger of putting the I after the square root? What do you think? Say it again. Yeah, sometimes you don't like to put stuff after radicals because if you're sloppy when you write it down on paper, sometimes you can't tell if it's inside or outside the radical, right? So this is correct, and it wouldn't be marked wrong on Math Excel if you wrote it that way. But where should we probably put the I then? After the 4 maybe, yeah. So typically what we'll do is we'll just put that I in front of the radical, and we'll just rewrite this as 4I times the square root of 2. But either way, it doesn't really matter. That's just, if you see it that way, don't be confused. That's why. This is a little safer to write it that way is all. Okay? All right, so I got a little trick to show you here. I think I've already showed this to you. When we were simplifying, yeah, I definitely already did. When we were simplifying square roots, remember we found a way, like if I did the 192. Okay, I know on the 192 one here, the square root of negative 192, I know I'm just going to get a simplified radical, and I'm going to go ahead and put the I at the end this time, times I, because I've got a negative there. Remember how to do this on a graphing calculator or on Desmos? I could just set up a function that's the radicand, the 192, whatever's under the radical, divided by x squared, and just go down the list until I know I've got a number in the right column, right, that I know is not going to give me any couples, right? And so this tells me that 192 divided by 8 squared is 3, right? So 192 equals 8 squared times 3, in other words. So I'm going to get a couple of 8s and a single 3. The left column always gives me the couples. The right column always gives me the singles, right? So then we could just write our answer here as 8's the couple, 3's the single, and I get an I at the end. Okay, if we want to use that little technology trick. Okay, give me 1 to 5 so far. How are we doing? Okay, all right. And right, that's all we just did. Okay. Okay. All right, so now let's look at some patterns here of powers. Well, so if we go back to our earlier example, we already did most of the work. I actually think we already finished that, didn't we? Yeah, we already finished it. Plus or minus 3i is our answer on that one. I'll just get rid of that page. There we go. So powers of I. Now, the way the notes go through this, they show you something interesting. But before we jump into that, I'm going to give you an easier way to think about these powers. And we can use it to fill out this table. But we know that I squared is equal to -1. Okay? Agreed? So what can you tell me about powers of -1? And fill in the blank here. An even power of -1 is what? Equal to what? -1, the quantity -1 taken to an even power is always equal to what? Like what's -1 to the 10th? -1, the quantity. So if I wrote this down, here's what I'm asking. What is what's -1 to the 10th? It's 1, yeah. How do you know that? Because -1 to the 10th, isn't that the same thing as -1 squared to the 5th? Right? Everybody agree? And what's -1 squared? 1. So -1 to any even power is always going to end up being some power of 1, isn't it? Everybody agree? Because I could always, if you think about it, there's another way to think about that. If I have an even power of -1, it means I'm multiplying a string of -1s with an even number of -1s. They would always pair up in couples, wouldn't they? And each couple would multiply to a 1. Okay, now what is, on the other hand, what is -1 to the 931st? It's -1, isn't it? Right? How come? because negative 1 to the 931st is the same thing as negative 1 to the 930th times negative 1 to the 1. And negative 1 to an even power, you just told me, is always equal to 1, right? Okay, so we got an interesting conclusion here then. Negative 1 to an odd power is always negative 1, and negative 1 to an even power is always positive 1. Okay, well, we could take advantage of that when we're trying to find powers of I. What if I had something like, for example, say I had I to the 37th. Actually, let's not do that one first. Let's do I to the 38th. Okay. What is I squared equal to? By definition? Negative 1. And you see why that is, right? Because if I square root both sides, I get I equals the square root of negative 1, which is our definition of I, right? Okay? So I could write I to the 38th. I could write that that's an even power of I. So I could write it as I squared to what power? The 19th, right? Is that, well, no, does that make sense? Because if I take a power to a power, I multiply the exponents, right? So I would just divide 38 by 2. Does everybody get that? Okay. And because it's an even number, I was able to do that, right? So I squared is what again? Negative 1. So this just devolves to negative 1 to an odd power. So what's the answer? Negative 1. Right? Okay, how about if we do I to the 100th? Can anybody tell me what that's going to be? What's 100 divided by 2? 50. Yeah, the answer's going to be 1, isn't it? So I'm going to get I squared to the 50. Well, that's equal to negative 1 to an even power. What's negative 1 to any even power? 1. Right? Okay, let's go down and try another example. I need some more room. How about down here? So let's try something like this. What if I have I to the 21? Okay, now that's different, right? 21 is odd, so I can't divide it by 2, right? What I'd have to do here is I'd have to say, okay, 21 is the same thing as I to the 20th times I, okay? But I to the 20th I can deal with. I to the 20th is I squared to what power? The 10. Okay, so what's my strategy shaping up to be? If I'm taking I to an odd power, I'm going to multiply the I to the even power immediately below that odd number times I. And then I'm going to take I to the even power and simplify that. Okay, so this becomes I squared to the 10th times I, which is just the same thing as negative 1 to an even power times I. So what's my answer going to be? Negative 1 to an even power is 1 times I is just I, right? Okay. Okay, let's try one more. One more here. So how about if we have a new color? I to the, what did I just do? I did the 21, right? Let's do I to the 31. Okay, talk me through the steps here. What's my first step going to be? Say it again. Okay, but I is not equal to negative 1. I squared is, right? Okay, there you go. So first step is going to be, we're going to write this as I to the 30 times my oddball I, the leftover I. Okay? I to the 30 we know is going to turn in, there's only two possibilities. If I have I to an even number, it's either going to be 1 or negative 1, isn't it? Right? Well, in this case, we're getting I squared, which is negative 1, to what power from the I to the 30? 15 times my leftover I. Okay? What's I squared? You guys have already told me 1,000 times. That's negative 1. So what's negative 1 to an odd power? Negative 1. So my answer is going to be negative I. Okay, we just went through all 4 possibilities. There's only 4 different outcomes you could get if I take I to a power. What were those? If I took I to an even power, I either got negative 1 or 1. Okay? If I took I to an odd power, I either got I or negative I. That's it. Those are my possibilities, right? Everybody get that? You know if it's an odd power of I, you're getting I on the end, for sure. It's just going to be I to an even power times I, right? Okay, so you guys work through, try this one on your own. Let's try I to the 15th. You can work with your neighbor if you want to. That's fine. What'd you get, Aubrey? Did you get an answer? Correct. Negative I, right? Negative I. Okay. So how did we get that? I to the 15th is I to the 14th times I. I to the 14th is I squared to the 7th. And I squared is negative 1. Negative 1 to an odd number is giving us our negative. And then we're going to have this leftover I because we had I to an odd power. And that's it. Okay, you can do that in your head pretty easily, right? How do I do that in my head? I just look at the exponents. 15 minus 1 is 14. I to the 14th is negative 1 to the 7th, right? I always just end up dividing that even number times 2 to figure out what power I'm taking negative 1 to, right? So I can see right away that half of 14 is odd, so I'm going to get a negative number in front, okay? And then my original power was odd, so I'm getting an I tagging along, a leftover I on the end. Okay, give me 1 to 5 on that. How are we doing? Okay? Okay, good. I'm probably overdoing this. See if you can do 14 in your head. Everybody, try that. When you got an answer, just raise your hand, somebody. Let's see what we got. Okay, what do you got, Carson? Negative 1, sure. How come? Now it's an even power of I, so I got no leftover, right? I'm not going to get an I in my answer. Half of 62 is 31, which is odd, right? So I get negative 1 to an odd power, which is negative 1. Right? I would say you could skip all the way down to here, okay, in your head. Okay. All right, so if we follow, there's going to be a pattern here, isn't there? If we look at I to the 1, I to the 1 is just I, right? There's nothing we can do with that. I squared is what again? Negative 1. Oh, darn it, I won't do that. There we go. Okay, is negative 1. What about I cubed? What's that going to be? Negative I. How come? Because it's I squared times I to the 1, isn't it? So I'm going to get negative 1 times I, which is negative I. What's I to the 4th going to be? Say it again. Negative 1? Thumbs up, thumbs down? Al, you want to change that? Positive 1. Yeah. How come? Because it's I squared squared, right? 4 divided by 2 is 2, which is even. So I'm getting negative 1 to an even power, which is 1. When I go up to I to the 5th, a couple ways I could think about this. I could think about it as I to the 4th, which is 1 times I, so I'm getting I. Or I could think about it as, I to the 4th, even if I have to remind myself what that is, that's an even power of I squared, isn't it? So I know I'm getting 1 times I is 1. I to the 6th is giving me an odd power of I squared. And that's not the way I showed it here. I don't like this way as well. A better way to do this would have been like this, wouldn't it? It just would have been to say I to the 6th equals I squared cubed, right? So negative 1 to an odd power is negative 1, right? I to the 7th is I to the 6th, which is negative 1, times I, so I'm getting negative I. Right? That's not the way it was shown on here, but that'd be an easier way to do it. I to the 6th times I. And then I to the 8th would just be I, see again, that's not the best way to do it. It'd be I squared to the 4th would be a better way to do it. So an even power of negative 1. But what do we notice here? We get this cycle, don't we? Every 4, it just cycles through these different values. Every time I ratchet up the power of I by 1, it's just going to go through the cycle over and over and over again forever. Okay? All right. Next issue. Okay? Multiplying imaginary numbers. Okay, multiplying imaginary numbers. What if we want to do 4i times 7i? How am I going to do that? 11i. What's it going to be? 11i. Okay, now I'm not adding, I'm multiplying. Now, if you were adding, you'd be right. 4i plus 7i would be 11i. That's absolutely true. What's 4i times 7i? 28 I squared. And what's I squared? Negative 28. Okay, now how are we doing this? So we're treating, when you're multiplying, when you're doing any arithmetic with i's, okay, where you have imaginary unit in there, always just treat that like a variable until you get to an I squared, and then you know I squared. That's not like an x squared. That means something. I squared is negative 1. So we could do this. Like 4x times 7x, you could all tell me is 28x squared. How did we do that? Because we just commuted. I'm going to write this down one time. After that, we won't need to. I could just rearrange the order in which I'm multiplying stuff. Right? I could multiply the 4 times the 7 times the I times the I. Right? And then that's giving me 28 times I squared, which is equal to negative 28, right? You can skip a bunch of steps, though. You just know it's 28I squared, which makes it a negative 28. Okay, how about up here? What am I going to get? Bunch of ways we could do this. We could multiply it together like the numbers, the product of the numbers times I cubed. Or maybe even easier, let's just do this in pairs. What's that green pair going to give me? What's negative 4I times 2I going to be? Say it again. The answer is 8, isn't it? Negative 8I squared, right? But what does I squared do? I squared is negative 1, so anytime I multiply an I squared, it's just changing the sign of that number, isn't it? Everybody get that? So this looks like negative 8 I squared is what all that stuff multiplies to. And the I squared, all that's going to do is just change that sign to a positive 8, right? So all that stuff just becomes an 8. 8 times negative 9I is what? Just treat the I like a variable. What do you get? Negative 72I. That's it. Okay? No big deal. Right? How about 17? The quantity 2I cubed times 5I. Well, first of all, let's simplify that part. What's our property of exponents here that we use? If I take a times b to the n, what's that equal to? A to the n times b to the n. Good. Okay, so this is equal to, if I take this whole thing, that's equal to 2 cubed times I cubed. 2 cubed is 8. I cubed. Think about I cubed now. That's I squared times I, right? What's I cubed going to be? Negative I. Good. So that's just giving me negative 8I times 5I. So what's that going to give me? I get negative 40I squared, which becomes 40, right? Everybody see that? The I squared is going to change that back to a positive. Okay, give me 1 to 5. How we doing? Okay. Okay, how about something like that? Number 20. So we want to simplify each one of these things, right? Square root of 24, negative 24, is going to give me, I've got to deal with my square root part. What's the square root of 24 going to become? See if you can just do that in your head. Two square root of 6. Good? Everybody get that? 2 radical 6. Okay, so this part's giving us 2 radical 6. The negative inside the radical becomes I. Okay, times square root of negative 3. Well, square root of 3 can't be reduced, so that's just going to be square root of 3 times I. And then square root of negative 2 is just square root of 2 times I, right? And now I just multiply these 3 numbers together in any order I want to. So let's take, how about if we take these 2? Square root of 3i times square root of 2i is what? Square root of 6. I squared, which is negative square root of 6. okay, times 2 times the square root of 6 times I. Okay, well now what do we got? Let's multiply these numbers together. 2 radical 6 times negative radical 6. Square root of 6 times square root of 6 becomes what? 6. And I'm going to have a negative 2 times 6 times my I. Can't forget that I. So my final answer on this one just looks like negative 12 I. Good? Okay? Okay, that gets us, that's a good stopping point for today.